All right, here's question 2 on the math subject GRE practice test 3768. So in this problem, what we're asked to do is evaluate this infinite sum. I suspect that what the test makers had in mind for this problem was for you to recognize that this sum is very similar to a common Taylor series expansion. You could reasonably solve this problem without recognizing that, but I'm pretty sure that that's what they had in mind. So maybe we'll first solve it that way. If you're going to be able to recognize a Taylor series expansion, well, it's a good idea to memorize some of the more common ones. I think the most common Taylor series expansion is just the geometric series formula. This is not the Taylor series in this problem, but I remember this was on the last GRE practice test. And it's definitely a formula that you'll want to have memorized, or at least know how to derive. It's a pretty simple derivation. The second one that I'd recommend memorizing ends up being the one you need for this problem. It's the Taylor series expansion for an exponential. It says that the function e to the x is just equal to the infinite sum of x to the n over n factorial. And what's really nice about this second one is, unlike the first one, the radius of convergence is infinite. But before I get into that, a couple more Taylor series that you might want to have memorized are the sine and cosine Taylor series. These are really nice because their formulas are so similar. Either way, we're alternating between positive and negative terms, where the terms are fractions, where the numerator is x raised up to some power, and the denominator is the factorial of that power. All the even powers, you can think about this as x to the 0 over 0 factorial if you want, show up here in the cosine sum, and all the odd powers show up in the sine sum. If you have a hard time remembering which is which, just remember cosine's an even function, and sine's an odd function. Or I guess another way you could do it is change all the x's into zeros, remembering that cosine of 0 is equal to 1, and sine of 0 is equal to 0. Anyways, there's a lot more Taylor series, even more Taylor series that you might qualify as common, but I'd be fairly surprised if the test makers expected you to have anything memorized other than these 4. And for this specific problem, we're only going to need this second one. I should point out that this first Taylor series expansion is a little different than these other 3. For this one, the radius of convergence is just 1. We need x to be between -1 and +1 in order to kind of use this formula. Whereas down here, the radius of convergence is infinite, so we can plug in whatever the hell we want for our value of x. That'll be really useful because if you stare at this second formula right here and you stare at the problem that they gave us, really the problem that's given is exactly this second formula, except in place of x, they're plugging in 3 log 2. 3 log 2 is a real number, so this formula holds with 3 log 2 in place of x. What I'm saying is the sum from n equals 0 to infinity of 3 log 2 to the n power over n factorial would be equal to e raised up to the 3 log 2 power. All we need to do is figure out which of these answers is equal to e raised up to the 3 log 2 power, and we're done with the problem. Couple comments here. Remember that anytime you see log on this test, it really means natural log. I kind of prefer to write it this way. When I write log, I think log base 10. When I mean natural log, I write ln. But for this test, when they don't specify the base and they write log, it means the base is e. It means we have a natural log. And that's really nice because when the base of your exponent and the base of your log match up, things simplify really nicely. To do that, we just need to apply a log rule. 3 of them that I'd recommend having memorized for this test is that the log of a product is equal to the sum of the logs. The log of a quotient is equal to the difference in those logs. And the log of an exponential expression is equal to that exponent times the log of the base. This third log rule is the one that comes into play for this problem. And you might be like, oh, right, because we have an exponent and this is an exponent kind of. No, not at all. Really what's going on is this 3 natural log of 2 is the right side of this equation. So this third log rule says that we can rewrite this as the natural log of 2 to the 3rd power. In other words, the natural log of 8. That's really useful because if I come up here and I replace 3 natural log of 2 with the natural log of 8, I have something that simplifies really nicely. The e and the natural log, kind of loosely speaking, cancel out and you're left with this 8. The reason that works is because if you think about like definitionally what the natural log of 8 means, the natural log of 8 is the exponent that you need to raise e up to turn it into an 8. So you got an e, and you're raising it up to some power. Oh yeah, what power am I raising it up to? You're raising it up to the power that you'd need to raise an e up to change it into an 8. So an e raised up to the power that you need to raise e up to change it into an 8 is equal to, well, 8. E is the answer to this question. I mentioned at the start of this video that I don't love this problem because it all relies upon you recognizing or memorizing this Taylor series expansion here. Just for the hell of it, let's pretend that you didn't have that memorized and you came into this test. Could you still solve this problem? Well, the answer is yes, kind of. I mean, when you have infinite sums like these, if they're going to converge, which they need to in order for you to answer this question, they typically converge pretty quickly. The factorial grows a lot quicker than this exponential growth. So the denominator gets big quicker than the numerator. So as n gets large, the fraction gets smaller. Most of the value of this infinite sum happens for relatively small values of n. So if you get lucky and the answers are somewhat spread out, you might be able to ballpark this and figure out the answer. You might be like, nah, I could never do that because I don't know what 3 log of 2 is. Okay, that's fair. But remember that 3 log of 2, or 3 natural log of 2, is equal to the natural log of 8 using this third log rule. And the natural log of 8 is just asking you the question, what power do you have to raise e up to change it into an 8? Well, e is roughly what, 2.7? 2.718 if you want to be a little bit more precise. So since e is less than 3, e squared is going to be less than 9. It'd be really nice if e squared were less than 8. That might help me ballpark this thing. Well, let's see, 2.7 is less than 2.8, and 2.8 squared. Do some quick multiplication off to the side because I'm not allowed a calculator for this test. 8 times 8 is 64. 8 times 2 is 16 plus the 6 gives me 22. 2 times 28 is 56. Looks like 2.8 squared is what, 7.84 if I'm doing that math right? What that means is since e is less than 2.8, e squared is less than 7.84. And what that means is the natural log of 8 must be greater than 2, right? Because the natural log of 8 is asking me what power I have to raise e up to change it into an 8. And I'd have to raise it up to a power bigger than 2 because when I raise it up to the power of 2, I get something a little bit less than 7.84. I need it to be bigger than this. I need it to be 8. I'm going to need this exponent to be bigger. The natural log of 8 is greater than 2. That's really nice. That allows me to bound this. I can replace this 3 log 2, in other words, the natural log of 8, with the number 2. I don't know, maybe down here, right? If 2 is less than 3 natural log of 2, then every term in this expansion is less than every term in this expansion. So this sum is less than this sum. The nice thing about this thing is it's relatively easy to compute. Change all the n's into zeros. I get 1 over 1, in other words, 1. Change all the n's into 1. I get 2 over 1, in other words, 2. Change all the n's into 2's. I get 4 over 2, in other words, 2. Note we're already up to 5 here. I change all the n's into 3's. I get 8 divided by 6, in other words, 4/3. Wait a minute, I was already at 5, and I just got 1 1/3. This right here is 6 1/3. It's already greater than 6. What I'm saying is by just considering the first 4 terms of this sum, I can tell that this infinite sum is going to be greater than 6 1/3, or more importantly, greater than 6. And since this sum is bigger than this sum, I know that this sum right here must be bigger than 6. If you go back up to your answers here, there's only one answer that's bigger than 6. It's E. You might argue that I got a little bit lucky that there wasn't an answer F, right? That said 10. Because if there was an F that said 10, I'd be like, I don't know if the answer is E or F. That's true. But I'd argue that we narrowed it down instead of 6 choices to 2 choices. And if we consider a few more terms, n equals 4, I get what, 16 divided by... What's 4 factorial? 24. N equals 5. I get 32. Divided by 24 times 5, 120. This is the limits of my mental math. 16 24. So if I reduce by a factor of 8, I get 2/3. 32 1/20. What, those both got an 8 in them, right? This is 4 times 8, and this is 15 times 8. After the first 5 terms, I'm up to 7. My 6th term is only 4/15. I'm getting pretty damn small here. This factorial growth down in the denominator is making these fractions really, really small. I've gone from 6 1/3 to 7 and a tiny little bit, 4/15. You might be able to just look at these numbers and kind of tell that they seem to be converging to something pretty damn close to 8. They don't converge to exactly 8 because remember, this is this sequence, which is smaller than the sequence in question, which we know converges to 8. But since we bounded things so closely, since 3 log 2 is so close to the number 2, this was a pretty good estimation for this value, and we can almost see the convergence in question. Would it be worth doing all this on the test? I don't know. I mean, time is definitely important on a test. It would be a lot better if you could recognize the Taylor series and make this question a lot quicker. But the point that I'm trying to make is if you didn't recognize this Taylor series, you could ballpark this infinite sum by considering the first few terms in the sum and take advantage of the fact that typically when things converge, they converge pretty damn quickly. So you don't have to look at a million different terms. Often the first 2 or 3 or 4 will be enough to give you a pretty good guess of what the answer is going to end up being.